Hello and welcome back to this second week of classes of the NPTEL course on principles of polymer synthesis. Just to recap what was discussed in the previous week, we started with a discussion of the historical development of the polymer science, and we emphasized upon the fact that polymers were known for a long time. Even in the early 19th century, polymers were prepared, except that the structure was not established. And not only that, even as late as early 20th century, people used to believe that it is the colloidal aggregates, association of small molecules, that is actually responsible for all the properties of the polymers. For example, the high melt flow or high melt viscosity, or material which sometimes you cannot crystallize, those kind of properties. So, they used to believe that this is the reason, and as we also had told that rubber used to be believed to be composed of cyclooctadiene, dimethyl cyclooctadiene monomers. They were actually having interaction with their double bonds with all these units together, and that was what was believed. So, then in came Dr. Hermann Staudinger in the early 1920s, and he was the person who coined the term macromolecules. Mind it, he did not coin the term polymers. The term polymers was known from 1833, that was actually coined by Berzelius. So, it was Hermann Staudinger who introduced this term macromolecule, and we have discussed about the resistance that he had to face from the scientific community, because crystallographers actually believed that these kind of long molecules, if they actually crystallize, how this full molecule can be incorporated into a small unit cell. But later on it was established by Staudinger and other scientists, the crystallographers themselves, that the full molecule does not need to be incorporated into the unit cell, a part of it will do. So, those kind of studies were done, and that was the discussion of the first class, and afterwards we had a discussion on the classification of polymers based on their structures, based on their mechanism, based on their properties, and also based on their sources. And then the discussion moved to the molecular weight of polymers, and we emphasized the fact that molecular weight is very important thing that we need to characterize for the polymers, and different average molecular weights were introduced, and some of the main techniques were discussed. And you will see that we have not discussed all the techniques. That will be the motto, that will be the theme of this course all throughout, that whatever are the basics, some of the most important things that will be discussed, and not all the detailed different aspects of, say for example, we talked about molecular weight determination, average molecular weight, weight average molecular weight. We talked about light scattering, we did not go into details. We talked about GPC, there we discussed things in detail. So, certain things we will discuss in as much detail as possible in a very simple and basic way. So, that will be the theme of this class all throughout. So, this week we are going to start with the topic principles of step polymerization. So, if you recall, when we classify the polymers on the basis of structures, we could say they are addition polymers or condensation polymers, or on the basis of the mechanism of formation of the polymers, we could say they are step polymers or chain growth polymers. And briefly we discussed what are step polymers or step growth polymers, or step growth polymerization process, and what is chain growth polymerization very briefly. But for now we will shift our attention completely to step growth polymers, and later on we will come to the chain growth polymerization, and the comparison of that will be also discussed in more detail probably. Okay. So, let us then start with step growth polymerization. The reason it is called step growth is because it is basically monomers which have more than one function, and these functionalities they are reacting among themselves. Either they will belong to one monomer or they will belong to different monomers, we will explain in a short while. And this reaction between different functions that happens in a stepwise fashion. So, what do we mean by that? So, what we can have is, for example, we can have a monomer, say we can have a monomer like this, a diamine. R is some generic term, it may be an alkyl group or long alkyl chain, maybe some aromatic units or whatever. And let us say we are trying to create a polyamide. Also, the reason why we will study the step growth in detail is many important industrial polymers are prepared through step growth polymerization. Same is also true for chain growth polymerization processes. So, for example, first when you are applying step growth principle, you can synthesize polymers such as polyethylene terephthalate, which is a polyester, or you can synthesize, you may know about the name nylon, it is a household name, I would say. So, those are a class of aliphatic, those are actually a class of polyamides which are aliphatic polyamides. So, those are synthesized through step growth polymerization. Or for example, bisphenol A carbonate. So, those kind of polycarbonates also, those are also polyesters, those are also synthesized by step growth polymerization. Okay, let us say we want to synthesize a polyamide. So, in that case what we can do is that we can take a bifunctional or we can take a more than bifunctional polyfunctional monomer. So, this monomer has both the functions the same. Now, amide formation is between amine and carboxylic acid, that is the reaction. So, what you can have is that you can have a bifunctional monomer like this, both the functions are the same, and you can have a bifunctional monomer like this. So, you have a diamine and you have a diacid, and when they react they will form a polymer which has a repeat unit something like this. Something like this. Or what we can have also is that in the same monomer, so basically you are reacting a function amine, this amine function you are reacting with carboxylic acid function. So, this is basically then the reaction between different functional groups. Or what you could have is that the same molecule could contain both the functions. The same molecule could contain both the functions, and then what will happen is that this molecule if you take, so the functions will react among themselves between different molecules. So, in this case, so you can have something like this. So, it is the same molecule is actually reacting, it can be also called as self amidation. So, this carboxylic acid can react with the amine, so on and so forth, and then you will have a repeating unit which resembles something like this. Say n number of units, that is what I am just writing down, if it is n molecules of this and n molecules of this. So, that is in essence the point of step polymerization, that you will have reactions between different functional groups, and those functional groups could be present in the same molecule, same monomer, or they could be present in different monomers. And not only that, the reaction will progress in a stepwise fashion, which means that the functional groups will engage with themselves in a stepwise fashion. So, maybe this monomer reacts with this monomer initially to create something like this. So, you will have NH CO. So, you have an amide unit now, R prime CO2H. So, it is a dimer. Now, this dimer, you have a carboxylic acid here, you have an amine here. This could also now react with another molecule of, let us say, amine on this side, and it can form an amide bond here. Then what you will have is a trimer. I am not drawing the structure, you can work it out yourself. So, like this, stepwise the molecular weight of the product will develop. So, this trimer can react with another dimer, or it can react with monomer itself. So, what will happen is that very soon in the reaction process, most of the monomer will be consumed, and you will have different kinds of oligomers. Different kinds means the numbers, say for example, you have trimer, tetramer, pentamer, decamer, so on and so forth. All these things will be present, and the molecular weight will develop slowly. Only towards the end of the reaction, that means when you have achieved a very high conversion, you will have molecular weight of any practical importance. So, when we say molecular weight of practical importance, we say at least 4000, at least you should have a minimum molecular weight, say for example you can have 4000, 5000, because if you remember the property versus molecular weight graph that we have drawn in the previous week, you will see that the properties will develop slowly and you need at least a minimum molecular weight in order for the properties to become significant in practical terms. But the question then is that, okay, so the molecular weight will be high, you want high molecular weight, but what do you mean by then control of molecular weight? I mean, then you would like to have as high molecular weight as possible, is that the motto? Actually that is not the motto. The motto is you want high molecular weight so that the properties that you want, they will be manifesting themselves in a practical way, a significant manifestation, and you want a range of molecular weights, a very as much precise as you can be, you want to be. So you don't want to be having a molecular weight higher than that. Why? Because if you want to go as high as possible, what can happen is that the processability may be affected, the melt viscosity may become so high that you cannot process the polymer. So that is very important to understand. So you have a molecular weight in mind, you want a certain molecular weight and you want to be as close to that as possible. So if you are looking towards that kind of situation, what you have to do is that you have to analyze the kinetics of these reactions, because if you can analyze the kinetics, then only you understand the principle fully, the mechanistic aspects of that fully, and then you know how you can control the molecular weight. And you will see that at least 99% of conversion is necessary from the monomers in the step polymerization, so as to have polymers of any practical significance. That means the molecular weight will be much low if you are say even at 95% conversion. 95%, 96% conversion may be very good when you are reacting small molecules and preparing small molecules in your simple organic reactions, simple organic transformations. But say 90%, a conversion of 90% is a disaster in step polymerization, because you will have very low molecular weight polymer. We will discuss all these things. So you need to go beyond 98% of conversion, and you have to go sometimes beyond 99.5%, so on and so forth, in order to have high molecular weight, high enough that will meet your purpose. Okay. So to understand all those things, the first thing you should do is to try and analyze the kinetics of these reactions. So if you look at these reactions, I am just drawing a symbol like this, M is your monomer. So at any time you have to actually analyze all these reactions, that monomer will react with monomer to generate maybe a dimer. Now this dimer can react with a monomer to create a trimer. Trimer could react with another trimer to create hexamer, and again this trimer can react with dimer to create pentamer, so on and so forth. So all these reactions are occurring, and all these species will be present in different amounts, of course, at any point of time. So you have to then take into account all these reactions when you are trying to analyze the kinetics, which is a Herculean task. In order to simplify our analysis, what we have done is we have made certain assumptions. Say, what are the kinds of assumptions we have made? So firstly, the functional groups of the monomer have same reactivity. What do we mean by that? I will go back to the same reaction. Say you have a monomer which has both the functional groups the same. So when I say functional groups of the monomer have same reactivity, all I am saying is that the same kind of functional groups, because your monomer can have both amine and carboxylic acid, they obviously do not have the same reactivity. So if you have, say for example, a diamine which is your monomer, both the amines have the same reactivity. If you are making an ester, polyester, then you are reacting a diacid with a diol. Instead of NH2 you have OH. Both the OH, they have the same reactivity, and both the CO2H, they have the same reactivity in the monomer. Second thing is that the reactivity of these functional groups is not affected by the reaction of the other function. What this means is that suppose you have a diamine and you are reacting with a dicarboxylic acid. So, first assumption says that both the amines have same reactivity. Second assumption says if one of the amines have reacted, the other amine will still have the same reactivity. So, the reactivity of the other amine will not be affected by the reactivity of the by the fact that this amine has already reacted. And the third thing is that this reactivity of the functional groups will not depend on the size of the molecule. What that means is that, so at any point of time you will have all these species which has amines, which has carboxylic acids. Let us take an example of only polyamide say and explain all through with this, we stick to this particular reaction. So, what will happen, say you have say a hexamer, you have a decamer, or maybe you have an N-mer where N is maybe say 50, and say you have an amine at the end of that N-mer and another side you have carboxylic acid. Now, that amine, the reactivity of that amine will be the same as the reactivity of the monomer. So, just because the size of the molecule has become large, it will not affect the reactivity of your functional group. That is an assumption. Now, all these assumptions you can actually say this is basically called as an assumption of equal reactivity of functional groups. That is the assumption, equal reactivity of functional groups. So, you might very reasonably ask this question, is this actually true? When you increase the size of the molecule, does this not affect the reactivity of the functional group? It should affect, maybe it should decrease the reactivity of the functional group. Actually, experimentally it has been shown that that is not the case, and people usually believed that the reactivity is affected because for some other reasons, whatever the reasons might be, the polymerization was not progressing at the rate that they want. We will also discuss one or two points that relate to this particular aspect a little while later. So, let us take, of course, whatever I am going to draw here is not generated by me. This is an experimental result that just validates this particular statement of equal reactivity of the groups. More precisely, that the reactivity of the groups does not change with the size of the molecule. So, let us say you consider a reaction such as this small molecule So, you have a carboxylic acid like this and you are reacting with say ethanol. I mean for this reaction only the experiments, the data are there in presence of an acid catalyzed esterification reaction, and you are making your product which is an ester COOC2H5. Now, this particular reaction, so I am going to draw a table here. So, this is a homologous series of carboxylic acid, this reaction. So, if you have a table X versus K, K is the rate constant for this reaction. K is the rate constant, K into 10 to the power 4 because the value is small. So, you just multiply by 10 to the power 4 and scale accordingly. So, let us say X is 1. So, you have 1 CH2 unit here, then your K into 10 to the power 4 is 22.1. If it is 2, then it is 15.3, if it is 3, 7.5, 4, 7.5, 11, 7.6, 16, 7.7. So, you will see that initially when you are increasing the size of the CH2 from 1 CH2 to 2 CH2 to 3 CH2, the effect is enormous. The reaction rate is dropping, rate constant is dropping enormously. But just after first few units here, after that this effect is this situation is stabilized. So, after a certain size of this group is reached, the rate constant of the reaction is no longer affected much or significantly by the size of the molecule. So, this is one of the proofs that tells you that basically the functional group reactivity does not change significantly with the size of the molecule. I mean some of these assumptions will break down in case of special reactions. We will not discuss those, we will discuss in general for many of the step growth reactions. This is the truth that these principles are actually followed and this principle of equal reactivity of different groups will work. For many reactions it will not work. For example, if you have already reacted one of the functions, you have a diamine, say one of the amines you reacted, it might affect the reactivity of the other amine in some cases. There you should have special treatment, those treatments we are not going to cover here. Okay. So, now with this principle of equal reactivity, let us proceed to try and analyze the kinetics of this particular reaction. Let us say we will take a polyesterification reaction, we will try to analyze the kinetics. These assumptions actually simplify our treatment. So, in a generic way, let us draw out the reaction. So, you have the carboxylic acid and these reactions can be catalyzed by acid. So, let us say HA is your acid. So, these are typically reversible reactions, K1 and K2 are the rate constants of the forward and backward reaction. So, you will have something like this species and you have A minus. Now, this species can react with your alcohol. Now, when I am drawing this wavy line, that means it may not be your monomer, it can be some kind of oligomer or polymer which has an OH at the end of it and that is reacting with this intermediate. So, this is K3 and K4 and you have COH, OH, OH plus this intermediate, and in the final step what will happen is that this will produce your product like this. You have an ester here and then you will have water produced and you will have acid generated. Acid is your catalyst, it is generated back at the end. Now, when you look at this particular reaction, it has all this reversible sign here. So, these are typically equilibrium reactions, and in order to have a high yield of the product, what is essential is that you remove this water as it is produced, because then you can shift the equilibrium towards the product side. So, you should keep removing water, and then when you are doing that, essentially this second step and this last step they become irreversible, they can be treated as irreversible. So, K4 is much smaller than K3 and K6 is much smaller than K5. So, they can be essentially treated as irreversible reactions. The first reaction between this protonation, your carboxylic acid and this acid, this protonation is a very fast reaction and it is a reversible reaction, but the other two reactions could be regarded as, for all practical purposes it can be regarded as irreversible reaction. So, now what you can do is that you can follow the rate by simply looking at or following the disappearance of carboxylic acid, the rate at which it disappears. You could actually titrate it with a standard concentration, with a base of known concentration, and then you can see how it is disappearing. So, that is the rate of the reaction. So, the rate of the reaction is then minus, so rate of disappearance of your carboxylic acid. So, that is the rate of disappearance of carboxylic acid, and let me go back to the previous script. So, here you have to actually look at what is the rate determining step, and that will govern the reaction rate. The second step is actually the rate determining step. The first step is very fast, it is not rate determining. The slowest step in all the multi-step synthesis is the rate determining step. This step is the rate determining step. So, what you then have to do is follow this and draw the expression of the rate, and that will be then equal to your K3. So, this is K3 into this intermediate. Let me draw it like this for the sake of convenience, into OH alcohol. So, this is the thing, but this is an intermediate and you do not always measure the concentration of these things. So, you have to replace this with more convenient quantity, with a more convenient concentration. So, if you look at the first reaction, this is an equilibrium reaction K1 and K2, they are related by the equilibrium constant. So, for this particular reaction then you can write equilibrium constant for this reaction K is equal to K1 divided by K2, and that is equal to your COH whole 2 plus concentration divided by CO2H into HA. So, from here you can have an expression of this term, and that term becomes equal to capital K into concentration of CO2H into concentration of HA. So, equation 2, equation 1. So, if you replace this term CO2H plus here by this expression, then your rate becomes equal to K3 into capital K CO2H HA into OH. Now, what you can do is that this K3 and K you can club together in a constant. This K is capital, this is small k. So, let us club together into a constant small k, and then CO2H. Now, let us say you are taking equimolar quantity of the starting materials, then CO2H and OH the concentrations are the same. So, basically you can say this is CO2H whole square, and let us say you are not adding any acid from outside, so that the reaction is basically self catalyzed. That means, your starting acid itself is catalyzing the reaction, then this HA can be replaced by the concentration of CO2H. So, that will be then CO2H whole cube. So, if the concentration of the monomer is, instead of this you just put m concentration of the monomer, then this rate can be written as minus dm dt equal to k m cube. Okay. M is the concentration of the monomer, which will be equal to the concentration of carboxylic acid groups, which will be equal to the concentration of hydroxyl groups, the starting materials, because both of them are in equimolar quantity. That is what our assumption is to simplify this matter, which is M, let us say, and this is a self catalyzed reaction. We are now talking about a self catalyzed reaction. So, if you put this M here and you integrate, so you integrate from M0 initial concentration of the monomer to the final concentration of the monomer minus dm by m cube equals to k dt. So, you do the reaction from time 0 to time t, and then if you integrate and afterwards organize this thing, then what you will get is something like this. Okay. Let me draw this thing out here, m square minus 1 by m0 square. So, if you put it like this, self catalyzed reaction, that will be equal to 2 kT. Okay. Now, let us say P is the fraction of the starting monomer functional group that has reacted. So, you can actually say P is the extent of reaction, P is the extent of reaction. So, P being the extent of reaction, that is related to m by this, your m, the final concentration of the monomer, is equal to the initial concentration of the monomer minus how much has reacted, which is your m0 into P. So, that becomes equal to m0 into 1 minus P. So, if you replace this m by 1 minus P here and rearrange this thing, m0 square will come there, then finally what you will get is this expression 1 by 1 minus P whole square is equal to 2 m naught square kT plus 1, 2 m naught square kT plus 1. Now, is the time to introduce another concept which is very important for our analysis here, number average degree of polymerization. Number average degree of polymerization, which is denoted by x n bar. Now, number average degree of polymerization is nothing but the average number of structural units that are present per polymer molecule. So, basically this is nothing but N0 by N, where N0 is the total number of molecules to start with, N is the total number of molecules that are present after time t. So, if you are doing a step polymerization reaction, initially you have 2 monomers. So, when you are doing the reaction for a time t, you may have some monomer, some dimer, some trimer, whatever. So, everything is being considered within this degree of polymerization, and with respect to that you will divide that. So, N0 is the initial total number of molecules, actually they are the monomers, N is everything that is present, the total number of all those molecules after time t, and this ratio will give you the average number of structural units per polymer chain. In this case it is also considering say dimer, trimer in this particular situation, because dimer, trimer, all these things can be present after time t. All those things will be included in the summation when you are calculating the value of n. So, this is N0 by n. Now, if you consider the fact that P is related to n and N0 by this N0 minus n by N0, because this is the extent of reaction. So, N0 minus n by N0, and then if you replace that here, what you will get is that your Xn becomes equal to 1 divided by 1 minus P, which is nothing but Carruthers equation that relates the average degree of polymerization, number average degree of polymerization with the extent of reaction. So, if you are looking for a further explanation of Xn, so let us say you have 100 monomers, I am just making some simplifying assumption here. Let us say you take 100 monomer units to start with, and then at the end what you get is 2 polymer chains. Let us say you do not have any monomer left, then it becomes easier for you to understand, but even if you have monomers left, the principle is the same. 100 monomers unit, and then finally you have only 2 polymer chains. So, what is the average degree of polymerization? That will be 100 divided by 2 equals to 50. So, you have basically 50 monomer units per polymer chain. So, if you are reacting say ethylene glycol with adipic acid, and then you have this kind of repeating unit CH2 CH2O CO polyester CH2 whole 4 CO like this. Now, here what is the value of Xn? Each repeat unit is actually containing 2 structural units. So, this is a structural unit that is donated by one monomer, this is another structural unit that is donated by other monomer. So, each repeat unit, this is one repeat unit, it contains 2 structural units. So, you have total n number of repeat units. So, your average degree of polymerization is nothing but 2n. Okay, so I think our time is up for the day. In the next class, we will continue from this derivation where we left it, and then we will derive the full kinetic expression and try to understand the significance of that in our further understanding of the polymerization, step polymerization. Thank you.